Good afternoon. My name is Paul Field. I'm on the Saturday Physics Series Committee. And it's my pleasure today to introduce Tokamak. But before I do that, this is a monthly program. The next one is October 19th. Professor Joe Berry from this department, who's a world expert in photoelectric energy conversion. So he'll be here. Probably in the same room, but at the same time, 2:30 in the afternoon on the 19th. So Oak is one of our most distinguished graduates. When I was chair of the department, Oak was the outstanding graduate from the department in the major college, the College of Engineering major, engineering physics. We have degrees offered in both arts and sciences and in engineering. So we have physics and engineering physics, and there's also an astrophysics degree that we are part of with the astrophysics department. Oak was our outstanding graduate when he graduated 8 years ago. In addition, he was the outstanding graduate from the entire College of Engineering that year. So we were very proud of him for that. And he earned Silicon Valley. He did an honors thesis with us with Toby Munsack in our department, currently our chair. And it was the Cosmic Dust Accelerator on East Campus, and I'm told that he made an ice creating machine inside the vacuum chamber so that they could test the effects of cosmic dust on asteroids and comets and the like. So he also minored in applied mathematics and leadership studies. In addition, he was a Goldwater Scholar and an astronaut scholar at the same time. And he led the CU Ultimate Frisbee team for a couple of years. And one of those years, probably not while you were you were not the lead that year, but they won the national championship in Ultimate Frisbee around 2014 or so. So he went on from a distinguished career here. He studied plasma physics and earned a PhD at Princeton University. He's now on the staff at Columbia University as an associate research scientist, and he's going to talk to us today about plasma fusion and tokamaks. Thank you. I'll use the microphones. Oh, you want to use that? Yeah, why not? Yeah, turn it back to. Thanks, Paul. Right, so yeah, I am Oak, as you just heard. I was going to spend a little bit of time tracking through my history, but you've gotten more than I was going to say already, so thanks very much for the nice introduction. I'm a Boulder High graduate as well, for those in the room that might be in Boulder High, and I grew up really fascinated by physics all the way throughout CU. That's why I chose to major in physics there. During the beginning of undergrad, I worked at NIST, working on terahertz metrology, but this was really fun. It wasn't really my interest. I was always looking for something new, something to really capture my passions and to take me through the rest of my career. And that's when I read on phys.org some random news article about, back then, I think this was 2014, NIF, which is a laser system in California, published something saying they had gotten some sort of break even from some fusion reaction. And I was like, oh, that's cool. Let's do that. And quit my job at NIST and tried to go study laser plasma physics. I did this through a study abroad program in Germany, since there wasn't a lot of laser plasma here at CU Boulder. But while at CU, or while in Germany, I learned that lasers aren't necessarily where I want to be. I think they have great promise as a fusion machine, but they're not going to be the first thing on the grid. So I wanted to come back and study magnetic confinement fusion. And best way to do that was in CU to study plasma physics, which is how I ended up working with Toby Munsack, doing plasma physics and dusty plasmas in space, which is really great. Eventually, I went on to study more plasma physics at Princeton. And finally, I've come back to Boulder now. I'm living in El Dorado Springs, just 15 minutes south of here. But I work for Columbia. And the way I can make this work is because I work at user facilities around the globe. So I work at machines in California, in Massachusetts, in England, in Germany, etc. And all these are a big collaborative experiments. Fusion is really a global effort more than I think a lot of areas of science. And so it's been really fun to be able to live where I want to live and work across the globe in that manner as well. Sweet. So that's a little bit about me, just for some background. And we'll motivate fusion, I think, to start this off as well. This talk was targeted at high schoolers, and I see that most people here aren't high schoolers, so I apologize if you're aware that the population is growing already. The world population has been growing for quite a long time. And this is usually due, or primarily due to increases in technology, right? Increases in technology that let people survive beyond childhood, to increase our lifespan, to increase urbanization, to accelerate migration. All of these things come with an energy cost. So while our population is growing, so will the demand for energy. We can't just sit where we are now with the current energy and path forward to the future. We actually have to grow more energy over time. And we have to do so in this new realm that we're facing, which is the global warming, the climate change realm, right? Where a lot of these energy sources that we've been relying on forever produce a lot of CO2 emissions, which we know will be pretty devastating for us in the near future. There has been a huge uptick in renewable energies as well. And so you can see those listed at the top here. But one, they don't even come close to covering the total supply, right? Most of our energy still comes from CO2 sources. And they're only, a lot of these are only transient as well. So wind can only be on at certain times, solar can only be on at certain times. And so we have a problem. We need more energy. We're going to need even more energy than we have now. And we need it to be completely different than the makeup that we have right now. This is a huge gap in our technology globally. And just FYI, AI is making the news a lot right now. AI is going to make this problem worse. AI needs data centers, and data centers need energy, right? So all these new tech, we continue to develop new tech. All that new tech compounds this problem. And this is a huge modern issue, and it's one that physics can actually help answer. And to put this in a bit of perspective, beyond just climate change, beyond just the energy perspective, this is a study that was released in Scientific Advances in 2023, studying all of Earth's planetary boundaries. There's 9 planetary boundaries of which we can't really exceed, otherwise we're going to face devastating consequences. And we've already perturbed 6 of the 9 of them, and those are kind of listed around in this here, right? So climate change is just one piece of the puzzle. We also have a lot of other parts of our world that are going to be changing very quickly and very rapidly in the coming years. And this is actually causing anthropologists to study a new era, a new epoch, sorry, in the history of the Earth, the Anthropocene epoch. We are defining a new epoch in Earth. And this is a huge period of time, a period of time with huge unknowns. So it's not just the energy side, but there's a lot of stuff that's going on. And we need technology to provide a firm energy base in order to project us into the future and to make sure we can get past this transition that is coming imminently. There are a lot of ways to get energy. Many of them have been around for a long time. They all have advantages and they all have some disadvantages. None of them are perfect, as we might know. The CO2 producing sources, coal, oil, and natural gas, right? These are fairly prevalent. They're fairly cheap. There's a lot of stuff out there. This will last us in the order of 50 to 130 years, which is, I mean, a long time, but it's not long enough for humans, right? So eventually we have to get away from this. All of the existing renewable sources that we have some disadvantages as well. Well, they might have no emissions. They might be geographically limited in the case of hydroelectric or wind. They might be transient like solar, or they might be posing significant safety and political concerns like fission, which is a power source that we've had along for a long time. Fusion, which is what we're here to talk about today, is a holy grail, if you will, of energy. It has practically limitless fuel. We get it from the oceans. There's a lot of water in the oceans. And it's also equitable access, right? We're not limiting our supplies of energy to one country, one geographical region. Pretty much everybody has access to water. It's clean, doesn't have any CO2 emissions. It's safe. There's no possibility of nuclear fission type meltdowns. There's no possibility of a Hiroshima. And it complements renewables that exist right now with very well by providing large scale firm energy production. So what this means is that we could, in theory, just turn it up, turn it down like we do a coal plant. We're not reliant on the wind. We're not reliant on the day-night cycle. It's just there all the time. The optimal size for a fusion power plant actually tends to optimize right around our existing power grid supplies. So you can basically just replace coal plant with fusion power plant. You don't have to build a new energy system, which is a really big advantage. And then there's no long-term nuclear waste. Yes, there's some nuclear waste. It's mostly irradiated concrete, but it has a half-life on the order of decades rather than on the order of centuries or millennia as with fission reactors. And we can store stuff for 30 years, 50 years. That's okay. We can do that. It does come with one big drawback, and it's science fiction. It doesn't work. Well, yeah, but we're getting close. So today we'll talk about a little bit more of the motivation. What is fusion? Why is it so great? We'll talk about different strategies that people have been adopting to try to achieve fusion energy throughout the global landscape. And then we'll pivot gears a bit and focus on the one that I like the most, which is basically the mainstream approach to commercial fusion energy. This is the tokamak. And finally, at the end, we'll get into some new developments that have been happening in the past 5 years. This is negative triangularity, which might revolutionize our ability to handle power in these large-scale machines. If at any point you have questions, please just raise your hand. I'm happy to be interactive throughout this as well. Cool. So what is fusion? How's it different than fission? Both of these we study in school very often, right? Fusion and fission both extract energy from nuclei. They're atomic based. There is a core practical difference in that fusion is putting stuff together, you're fusing stuff together to make a big thing. And fission is you have a big thing and you're splitting it and to make small things. And both of these will release energy. From the perspective of building a power plant, what this means is that for fission, you have a huge volume of material, say a block of uranium or something like that, and you put rods into it to slow down the chain reaction. The whole point of building a fission power plant is to slow down the chain reaction that you have going already. Fusion is kind of the opposite. It's really, really hard to get fusion to start going. And so it takes a lot of effort to get it to start going. Once it starts burning, we could just fuel it like you do a candle in a wick or something. But you never have a huge mass of stuff sitting there and it's not going off by itself, which is the big fundamental difference in the safety. If you have a huge mass of stuff for fission, that means that there's a huge mass of potential energy that could do something with. For fusion, if it burns out, it just burns out and then it's off. The liquid's extinguished. So there's a huge gain in safety there. So how do these both make energy? How can we split atoms to make energy and also put atoms together to make energy? Well, it has to do with the nuclear potential of different elements. And so here on the right, we have the atomic mass of everything on the periodic table and the energy per nuclear particle on the y-axis. Stuff up here like uranium or lead or plutonium, if we go to a smaller atomic mass, we're releasing energy. We're going down in potential energy, and so we're releasing energy to the world. And so this is how a fission power plant works. We go down this train. At the bottom of this curve is iron, and everything smaller than iron actually wants to get bigger to release energy. So two hydrogens coming together to make the helium releases more energy than the helium nucleus has, and you end up producing net energy. And you'll note too that the largest difference here, the biggest slope on this line is from hydrogen to helium. So the gains we can get from fusion are significantly more per nucleus than we can get from anything on the fission side, really. This is hard though, because those are I mean, a hydrogen atom is basically a proton, right? It's a positive charge and a positive charge, and they really want to repel each other. So this Coulomb barrier is really strong for hydrogen atoms. And this actually rules out most fusion reactions, just impractical. The amount of energy that it takes to get it started, remember I said it's really hard to start a fusion reaction, it's basically impossible to achieve for anything down in this range. Which leads us for just a couple different viable reactions that we can use for fusion. There's this one up here, D plus T, deuterium, which is an isotope of hydrogen, plus tritium, which is an isotope of hydrogen. This is 2 mass and 3 mass hydrogen, making helium and a neutron. And there's a couple other variations of this as well. D and D can make 2 different types of things. Deuterium and helium-3 can actually fuse to make helium-4 and a proton. You can also have a proton fusing with boron-11 to make helium and some energy as well. And all of these create quite a bit of energy. But they all happen at different probabilities. Fusion is only ever going to occur by chance. We're not going to be able to hold a hydrogen atom and hold another hydrogen atom to combine the two slowly and make them go together, right? We have to have them slam into each other at high speeds, at high velocity to overcome the Coulomb barrier and to fuse into helium. So it only occurs by chance. And we can actually measure the probability that happened using this thing called the cross-section. So collision cross-section is basically the effective area of an atom as it flies by in space to another atom. And if they collide in this collision cross-section area, they'll fuse together if they have the right properties. And you'll see the reason I have DT up in green here is because this has the highest cross-section of any reaction that we can access with temperatures here on Earth. And so we need to get up to some critical center of mass energy, and then we can maximize our chances of getting fusion. But it does only occur by chance. And so in order to have stuff by chance actually turn into a reliable energy source, there are a couple of criteria that we have to meet. One, we have to have enough of it to ensure that the things are going to collide together. 2, they have to be hot enough to make sure that when they do collide, they have enough energy to overcome the cooling barrier. And 3, we have to hold it there for long enough that these things will actually happen. So we need something that's really dense, we need something that's really hot, and we need something that's stable. it needs to sit there while it's really dense and really hot and create these random chance occurrence reactions. And it turns out that the product of these three terms, the density, the temperature, and tau, the time, is called the Lawson criteria. And this criteria explains how you need to be, how dense, how hot, and how long in order to achieve fusion. And it's a product. Turns out it's a product. So you could go for something that's really dense at a lower temperature and a lower time. You could go for something that's really hot at a lower density and a lower time. Or you could kind of like try to maximize all three and find yourself in a sweet spot. But the product of the three parameters is what matters. On the right here, I guess it's on your right as well. We have some curves for a couple of those common reactions: deuterium, tritium, deuterium, 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 helium-3. And each of these curves has some trough in the density in the tau at a particular temperature at which we want to operate. So this temperature is the ideal temperature for that particular reaction. If we're targeting something like deuterium, tritium, which again has the highest cross section, then we want to be somewhere between 100 and 1,000 million Kelvin, which is a big number. So we tend in plasma physics to measure this with EV or keV, and it's about 10 keV. To put this in some perspective, that's basically the temperature of the sun. 16 million Kelvin is the center of the sun, 5 million Kelvin is the corona, and we want to be right in that range. So we're building a star here on Earth, and that's the technical challenge. When stuff gets this hot, it actually transforms into a completely new state of matter that we're usually not very familiar with. We have solids, we have liquids, we have gases. If you take a gas and you add energy, you actually end up ripping apart the atoms. So you take the electrons, you rip them off, and you have an electron and an ion flying around in space. And this state of matter is called plasma. Plasma is so hot that they form this ionized gas. And this is really the fourth state of matter. We take credit as 4 over all the other states of matter that particularly CU has a lot of expertise in the physics department, because plasma is 99% of the visible universe, which is a lot. We don't deal with it a lot here down on Earth because Earth is relatively cold. We're not in the center of the sun, right? We're dealing with solid things. But 99% of the visible universe is plasma. So a bit of an interactive challenge here, and maybe some prizes to give away as well. Can anyone think of examples of plasma? Lightning, yeah. Who else? Sorry. I didn't catch it. Quasars, yeah, sure. Stars in general can be, stars in general are plasma. Everything you look up into the space that emits light. That's a great one. Got a set of trading cards for you as well. Anyone else want to venture a guess at what is a plasma? Yeah, microwave grapes will explode in a little fantastic arc, and that split-second arc, that little lightning burst from the grape into the rest of the microwave, is indeed a plasma. Yeah, so there's lots of examples, some of which we're familiar with here on Earth. They're not that exotic. A couple of common ones that we didn't mention were neon lights down in Vegas. Here we have a picture of stars. The plasma balls, of course, if you can play with those, and Into the Wind down on Pearl Street, they have a bunch of those, plasma itself. So there's lots of stuff. There's also some pretty interesting technical applications of plasma. You use it all the time to make silicon wafers on computer chips. People are looking into plasma accelerators for rocket propulsion, using it to actually clean the environment by destroying a bunch of biological hazards with this really intense energy. And there's some recent work also using it to heal wounds, both to clean surfaces by distilling microbes, or to dig in as like a little plasma knife, as a microscopic tool. So our challenge today is that we want to build a sun on the Earth. And yeah, that's kind of hard. The sun uses gravity to achieve this triple product that we talked about. So it uses gravity to pull everything in, so it gets really dense. When it gets pulled in, it gets really hot. And of course, it's just getting pulled in all the time, so it's going to sit there for a long time, right? So we have really dense, we have really hot, and we have a long time. But stars are massive. If we were going to use gravity to build a fusion reactor on Earth, we would need a physics department that has a room that's about the size of the sun, which is not going to work. So that one we can rule out. There are a couple other strategies here. Magnets, which we'll talk about throughout the rest of the presentation mostly, can be a great way to do this. And this is magnetic confinement fusion. Plasmas are charged, which we'll talk about in a bit, so they respond to magnetic fields. We can actually use magnetic fields then to hold the plasma in place while we put more of it in, while we heat it up. And this can really lead to a great reaction, which is likely the leading approach for commercial fusion power. There's also lasers, which have made a ton of progress in the news recently. I heard some grumblings in the beginning before the lecture started of myth and breaking even in scientific gain. And this is a huge achievement for fusion. This is using lasers to blast in a tiny piece of material so that it gets to those instantaneous temperatures. Now, that's a really short time, right? So we have to multiply the product. So laser fusion gets to really, really dense, really, really hot conditions, but only for a short time over a small volume. So it's really, really extreme and pretty cool. I mean, I have a plot here kind of on the bottom. There's no axes, but the bottom is time, and the y is how much, or the vertical is how much fusion power they've made per experiment at the emissions facility in California. And it was 0 for a long time, and then recently, boom. Because once you pass this critical barrier and achieve break-even, you can really just start blasting the plasma, and it gets really easy. So lasers are a good technique as well. This is actually what the USS Enterprise uses to fuel its spaceship. And then there's mixed type of, I call them mixed magneto-inertial reactions as well. And these combine aspects of both. So aspects of some sort of magnetic confinement to hold things in place, some sort of compression to get stuff really dense. You can do this in a lot of different ways. And so there are a lot of different alternative concepts that can work in this environment, and a lot of them have some really great advantages. They might be smaller, or they might be more portable, or they might not create neutrons. So these could be really great fusion reactions, but they're likely second or third generation because they're more difficult to do compared to the mainstream approaches. So all these technologies exist. There are lots of strategies, but each of them has their issues to solve. None of these work yet in the commercial power plant sense. And I wanted to emphasize here as well that this is really a global project. I said at the beginning that I work on machines in several different countries. There are over 160 laboratories that have experimental plasma physics across the world, and they all communicate with each other. Sorry, experimental fusion physics across the world. They all communicate with each other on a pretty regular basis. This doesn't include the theory community at all. So if you want to take this number and multiply it by 2 or 3 or 4 to capture all the people that are doing computational model, analytical theory, it really turns into a really great environment. And from the practical perspective of the American Physical Society, say, plasma physics, and particularly fusion, really has its own national conference in the United States. So we've become this kind of self-sufficient community, which is really fun and a really great collaborative environment to be a part of. So what have we done in the past time that we've been trying to do this, about 40 years? We've actually made a lot of great progress. So if you look at back where we started, this is a bunch of different types of machines, a bunch of different experts, hundreds and hundreds of people in this work. But if you look at back at where we started, and then project that towards where we want to be, this is as a function of time here, and the triple product is on the y-axis. We're getting better and better triple products, and we're getting up to values of q equals 1, q equals 2, q equals 10, q equals infinity. So this q turns out to be a really important metric in fusion. Q is the energy output over the energy input. So if Q is greater than 1, we made more energy than we put in. And there are a couple laser pulses up here in the 2022 range, in which case that was actually done. There's a couple targets here. Q equals 1 is the scientific break-even. This is what we say, okay, we've done it in the science perspective, but there's still a lot of extra energy that might be wasted in the machine to get the energy to the actual fusion reaction. If you get about Q equals 5, the plasma starts to sustain itself by self-heating. And so this is called a burning plasma. This is what we want to achieve in a tokamak to keep it going and going and going and going. We just have to keep putting more fuel in, and eventually, if we take the fuel out, it'll stop. And Q equals infinity actually happens really quickly after Q equals 5, because you just keep making more and more energy. Q equals infinity is ignition. This is runs entirely self-sufficiently without any sort of external heating. It's entirely reliant on self-heating. The energy input goes to 0. And this progress that we've made towards those values over time in the various fields is actually faster than Moore's law, which is the famous law, of course, of the number of processes we can put on a computer chip, which is often heralded as one of the great technological advances of our time. Fusion progress towards Q equals 1 has been a bit quicker than that. It's just that everything less than 1 is completely irrelevant. And so it's kind of like a binary thing. We can't slowly upgrade our computer chips. Looking at this same plot again, but now not having just the triple product on the y-axis, instead of breaking over temperature, you can kind of see how these different approaches break out in a new space. So up here is where we want to be. This is Q equals 1, 2, 10, infinity. And the laser plasmas are going to be at the top of this category. These are, again, very, very dense, very, very hot, but short time scales, like extreme conditions. These are likely more difficult to scale to commercial applications because you have to do a repetition rate. So you have to have 10 laser pulses per second, 100 laser pulses per second, which is a huge investment, not only in fusion technology, but in laser pulse technology and in facility generation, et cetera. There's one machine in the world right now that can make a pulse big enough to make inertial confinement work, and it takes it hours and hours to charge up, and it's the size of like 2 football fields. So it's very difficult to expand that towards where we want to go. But people are working on that problem and hopefully get there soon. Tokamaks are in this next generation, or this a little bit lower down on this plot. Magnetic confinement fusions is a broader category. This includes tokamaks and twisty tokamaks called stellarators. These are longer pulse, more steady state machines, so a lot easier to scale up, but they're at more moderate temperatures and more moderate conditions. Still on the temperature of the sun. It's funny, instead of the temperature of the sun is moderate, but that's the world of fusion. And then we have alternative concepts down here in the bottom. Again, this is more likely a second generation. You'll see a lot of startups these days propagating some alternative concept or something like that. These are likely specialty. They get investors because it's going to be aneutronic, or it's going to be modular, or it's going to be portable, or something like that, which is really cool and great technologies. And eventually, hopefully, they all work, but they're likely to be a little bit later to join the energy mix than these 2 mainstream approaches. So turning now, I think everything from here on out is mostly focused on the tokamak itself. So how do we use a tokamak, or a magnetic confinement machine in general, in order to sustain a fusion reaction? The trick is that plasma is very responsive to electromagnetic forces. If you remember at the beginning, I said it's an ionized gas, right? There's charged particles, negative particles and positive particles that are flying around in space. And all these respond to magnetic fields. So what happens through the Lorentz force, if we have a magnetic field in space, and we have a charged particle flying around it, it will spiral around the magnetic field line. And it will follow that magnetic field line back and forth. The drift away from that magnetic field line will be kind of small, and the drift along it will be very, very large. And you can see examples of this in space. For example, looking at the solar wind coming into the Earth's magnetosphere. It's propagating out from the sun, and eventually it hits our magnetic sphere that's generated by the Earth, and it starts to propagate around the Earth. If Earth didn't have a strong magnetic field, all of this plasma would come straight into the Earth's atmosphere, and it would be a different planet. It would be very different. This is seen in different planets that don't have magnetic fields in the solar system as well. Instead, we get plasma following these magnetic field lines, and it goes through like magnetic reconnection and things like that, and then eventually comes down, and all the plasma comes down the field lines into the North and the South Pole, which is actually why you see aurora in the North and the South Pole. The aurora borealis is plasma streaming into the atmosphere and creating light when the plasma hits the neutral particles in the atmosphere. And we don't see that around the equator because all the plasma gets funneled into the North and South Pole via magnetic fields. So we have a plasma, and it's following magnetic fields. If we want to hold it in place, all we have to do is make that magnetic field bite its own tail, right? So then our plasma is spinning around, and it gets to where it started. It's spinning around and gets to where it started. This is the shape of a donut, or the shape of a toroid, or any other shape where it just comes and goes in the same sort of system. So the tokamak is the simplest version of this. It's literally just the shape of the donut. It has a couple sneaky variations. It has some colloidal magnetic field, which is actually keeping the plasma spinning, which turns out to be very important for basic stability properties. But in general, the plasma is just going to run around the torus like this and keep going and keep going and keep going. So in an ideal bird's eye view perspective, it's kind of an infinite loop. We have the plasma there forever. To help with this, we actually layer the magnetic fields inside the tokamak like an onion. So you have a smaller magnetic surface in the middle, and that's comprised outside. There's another magnetic surface, another one, another one, another one. And it's really hard for plasma to go across those magnetic fields. It's a slower drift than it is along the magnetic fields. And so by having like layers of protection, we can keep the core plasma, which is the hottest part of the plasma, there for even longer. And these are the fundamental parts of a tokamak. You need a bunch of magnets to do that. The colloidal magnetic field, like I said, is really, really important. In a tokamak, we generate this by having a plasma current. So there's several mega amps, 10 mega amps, 15 mega amps of current running around the tokamak. And just due to your right hand rule, will have a magnetic field spinning around in the colloidal direction. The other more complicated design is to bake in that curvy magnetic field into the magnetic design itself. That's a stellarator. So a stellarator won't have any plasma current. Instead, we'll have these weird, funky shaped magnets, which I can show in later presentations if you'd like, which bake that twisty colloidal magnetic field right into the structure. And both of these together, the toroidal magnetic field and colloidal magnetic field, let us hold the plasma for a long time. If we're going to go look at tokamaks now, what we'll do is we'll take a cross section of the toroid. So imagine that this is our onion layer. Each of these lines, each of these white lines that you see is a magnetic surface. The plasma is going to spin around these magnetic surfaces over time. I've colored the dotted white lines outside of this main area differently because those white lines, still magnetic surfaces, interact with the wall, right? So there's a bunch of surfaces in the middle here that don't interact with the wall whatsoever. And this is basically an infinite loop. The plasma can stay there as long as it wants. But if it drifts out enough, it eventually hits the stick-like line, which is the first line to interact with the wall. Everything out of this is in the scrape-off layer, we call it, because it's not confined. The plasma will just spin around one of these lines and then hit the wall. For looking at the temperature gradients, the core, like we said, is insanely hot on the temperature of the sun, right? The edge has to get down much cooler. And then the materials, the walls, have to be metals. They have to be diagnostics even at liquid nitrogen temperature. So we have to go from the sun to sometimes the coldest place on Earth in the space of 2 meters, 3 meters. That's a huge temperature gradient, right? And this huge temperature gradient is a big source of free energy, which is causing a lot of the slow developments in fusion. This energy, propagates out from the core, and then it'll propagate it down along these open field lines until it hits the diverter. And handling these power fluxes is one of the key technical challenges for commercial fusion. In present machines, our plasmas aren't that hot, and so it's okay. We can have materials do this. But if we want to go to a reactor, suddenly we have to have plasma-facing materials that can withstand the amount of heat flux that's comparable to those experienced by a spaceship during re-entry. And it's really, there's no material in the world that can do that long-term forever. Tungsten is an insanely high melting point, but that will just melt away as the plasma comes in. So this is a big technical challenge we have to fix. I saw a question up here.
What are the source of the fluxes on the previous slide? Is the electricity or
Yeah, great question. So what is the source of these power the power fluxes? The goal of fusion, right, is to have a really hot, dense core. And so this hot, dense core is often made in a reactor. It'll be made somehow by self-heating from the plasma reactions, which will heat up more plasma around them. But in present-day machines, we actually have heaters. I think, on the next slide, I showed some heating mechanisms. So these heaters are going into the plasma to heat it up. And we try to aim the heaters. They can either be like a neutral beam of particles or a big fancy microwave. One of the two to heat up the core of the plasma, because that's the most insular in this onion that we're talking about, right? And I've talked about how plasma will follow the magnetic field lines, but in truth, it only does so 95% of the time. It also drifts away from the magnetic field lines. And so these inherent drifts caused by the big gradients that we have to sustain are going to push the power out. So we always have to be heating up the core, which eventually the plasma will do itself. But the power always has to leave. It can't just sit there, right? Power in and power out have to be equal. And so, just by conservation of energy or by power balance, we have the heat fluxes coming out from the hot core region. And I wanted to say also this word diverter, which is a big word that if you go looking around fusion, you'll see this. Fusion is full of jargon. I've saved you from most of it, but this is one you should know. The diverter is basically just this region where most of that power has to be handled. It's basically the trash can of the tokamak. And it's this region here where the first open field line is going to hit the machine wall. Cool. So in addition to heating the plasma, we also have to play some fancy tricks. And one of these fancy tricks is a physics thing called high confinement mode, or H mode. And it's basically a way where we can get the plasma pressure, the density, and the temperature as high as we can in the core to achieve fusion reactions. And we do this by adding a bit of really steep gradient right at the edge. And it turns out that this is an emergent phenomenon. So H mode or high confinement mode just happens under particular conditions. A plasma in a tokamak will always start in L mode. It'll always start in low confinement mode, which is just a plasma sitting there. And it turns out as you heat it past some threshold, so there's some power threshold, either PLH or FLH for the L to H transition, it bifurcates into an improved confinement state. We call this H mode. So in these pictures, these cartoons on the right here, what we're showing is a low confinement mode is basically a faucet, your core plasma dripping out until it gets to the bricks, which are plasma facing walls. What happens in plasma physics, because plasma physics is crazy, is when you turn this flow up, you turn the plasma up a lot, you turn it to a high pulse, a bucket will materialize out of thin air. It's a transport barrier. It's keeping the water from hitting the bricks. And this is really good because it gives us higher temperature, it gives us higher density, and it keeps the plasma there for longer. So it's a materialized bucket, a pedestal, which is absolutely fantastic for fusion conditions. And we can look at this in terms of plasma measurements as well. So here I'm showing the normalized radius. So how far out from the core of the onion to the edge of the onion we are. And we're looking at like 92% to 100%. So right in the edge region. And the plasma pressure here on the right in H mode, you can see is much bigger than the L mode, the low confinement mode. This is a self-emergent plasma phenomena. And so we get this big increase in the heat flux. And the physics behind this, why this happens, is that as you add more and more heating, you eventually get more and more electric field right in the edge region. And this creates the toroidal geometry, E cross B, electric field cross magnetic field, rotation frequency. And if you look at turbulence in the plasma, it'll be in these giant eddies. But if you're shearing away, if you have some rotation frequency in the edge, you're shearing away, these eddies get smaller and smaller and smaller. And eventually the eddies aren't big enough to talk to each other. So if there's these eddies that are going across the layers of our onion, moving our plasma over great distances, and we make those eddies really small, then it's a lot harder for the plasma to get from one surface of the onion to another surface of the onion. We end up with a transport barrier. So the shear in the electric field actually results into an enhancement of confinement in the core. And this is basically the underlying physics of how we go from low to high mode. We'll come back to that. I have another little pop quiz here. What happens in this scenario in real life? You go out to your backyard and turn your hose on. The bucket overflows. Yeah, the bucket overflows. And this happens in plasma physics too. Energy in, energy out. We have to eventually overcome our transport barrier. And we call this an edge localized mode. So we'll see if we can get this video to play. This is a video of a plasma in England that I work with. And you can see here kind of the shape of the tokamak, right? These colors are coming from when the plasma hits the gas and it's creating light, just like the aurora. And if we let it play, it's just sitting there, it's doing its thing, It looks nice and stationary, and then blammo, something happened right at the end. And this is what an elm looks like. We can see already in this picture of the elm, see if I can pause it. No, not quite, let's try it one more time. You can see some sort of toroidal variation in the, too soon. So that's the elm itself. We're connecting a ton of plasma to the outside, and it's making a giant little like burst of aurora, burst of power hitting the outside surface. And you can see it's following these twisty magnetic field lines that we described earlier. Yes, so this line you see here, this thin red line, is the same red line as the white line we're looking here. It's where the hot plasma hits the cold gas. It's a magnetic boundary. Yes, that's correct. Cool. Yeah, so these elms are periodic things. They happen every once in a while. You overflow your bucket, all your stuff gets lost, and you have to refill your bucket. You overflow the bucket, everything gets lost, and you have to refill your bucket. And it's a transient connection of the core, which is really, really hot, to the wall, which has to be really, really cold, similar to like a solar flare, if you want to use an analogy in space, where we have solar flares in our tokamaks. And these events in tokamaks can happen anywhere from like 10 to 100 times a second. As you might imagine, dumping your core plasma out onto your wall can be really hard on your plasma-facing materials. So you can see this kind of admitted here. This is the stored energy as a function of time. And each one of these big bursts in D alpha, which is our emission light, how big is our light? Each one of these bursts is an elm, and each time we have an elm, we lose a ton of our plasma. Then our plasma has to grow up again. Then we lose our energy, we lose our energy, we lose our energy, we lose our energy. And happens over and over and over again. And it turns out that this is okay on modern machines because our plasmas are kind of cold. But if we scale up plasma current and we scale up the energy in our plasma, it can get so intense, these solar flares can get so intense that they actually start to melt the surface of the material that we're holding in place. So this is the scaling of the energy in one elm as a function of plasma current, IP. And what we want to do, we're over here in like the 2 range right now. 5 is like a start of a reactor. 15 is where we think we need to be. And as we scale up, the energy in an elm gets so big that it starts to melt the surface of the power plant itself, which is really bad. And so this basically leads to the conclusion or the constraint that any tokamak fusion power plant cannot have elms. Elms must be avoided. And so we need some way to keep our plasma there to have the bucket, but then to not overflow the bucket in these giant periodic bursts, which is kind of tricky. And this is an example of one of these things happening in a controlled experiment. You don't want that in your day-to-day operation of any device. So we know that H mode is some emergent philosophy or phenomenon, and then when the bucket overflows, we get to elms, it spews a bunch of energy everywhere, melts our walls. Pop quiz. How do you fix an overflowing bucket? Put a hole in it. Good idea. Yeah. So if we can induce some extra transport, is what this is in physics terms, right? If we can induce some extra flow out from the core of the machine, we can have a bucket that still is holding some water, but it's flowing out at the same rate. And then we have the best of both worlds, question mark. So the real study here is that H mode is too good. The confinement is too good when the plasma does it by itself. And so we have to find a way to degrade it a little bit and make it a little bit worse. So this is where we get to negative triangularity, which is this new 5 years-ish development in the tokamak space. So if we're looking back at our picture here, what I mean by the triangularity of a plasma is related to the plasma shape. If you look at this plasma, it has kind of a flat end here and then a D-like shape. And we can exaggerate that flat end here in a D-like shape. If it looks like a D, the triangularity is greater than 0. If you flip the D around, the triangularity becomes negative. And so this is really just a simple shape change. We're changing our plasma from a D-like shape to an inverted D, if you will. And this has a lot of cool applications. One, already, it has more room for an advanced diverter. This is the inside of the toroid, and so it's compressed. And on the outside, we just have more space. So if we want to do something fancy with our power handling diverter, which is not the subject of this talk, negative triangularity offers some advantages to do that. So these plasmas were originally explored in the 70s and 80s, both experimentally and by modeling. But they were basically predicted to have worse stability, worse confinement, and so they were abandoned. Because in the 70s and 80s, we wanted everything to be as good as akin. Now that we have something that's too good, we have to back off a bit. There's renewed interest in looking at this regime. And you can see this in this sort of scan here. Plasma collisionality is just sort of a normalized parameter that describes a state. And so by looking at the x-axis over a function of states, we're looking at a bunch of different plasmas. The y-axis here is electron heat flux. So the more heat flux, the worse. The less heat flux, the better. And you can see here is a change of shape from positive delta equals 0.4 to negative delta. And again, we have little diagrams to illustrate what that looks like. Over this whole space, the negative triangularity has lower electron heat flux than it does in positive triangularity. And so this first sort of observation was really exciting, but it's actually been supported by a lot of recent work on a bunch of different machines. And so it's been really catching fire in the fusion industry. So there's a couple of points here. One is negative triangularity actually helps to confine your core plasma more. And this is because particles in a plasma tend to bounce. They have some amount of magnetic energy. There's some amount of energy total, and they're following field lines. And the field lines go from higher magnetic field to lower magnetic field because there's more magnetic field in the center of the donut. And so they only have enough energy sometimes to make it part way before they have to turn around and go back. It's like rolling a ball up a hill. If you don't have enough energy to go all the way over, you come back down. And so you're just rolling up and down and rolling up and down. There's this other thing that happens in plasma physics, which is a magnetohydrodynamic phenomena, where you have better stability properties in the inside of this line drawn in purple, which goes from the points of your D to the center of the D. And so on the inside of that, you have good curvature. On the outside of that, you have bad curvature. In positive triangularity, you might have some orbit bouncing between some minimum B and some maximum B that spends this entire time in bad curvature. That same orbit in negative triangularity will actually go into this good curvature region, which is better for stability. And it's slowest there because it's at the top of the hill of potential energy. And so it spends a lot of time in that good curvature region. And this actually has a destabilizing effect on turbulence, which is why you get that reduced electron heat flux. But in addition to being good for the core, it's really bad for the edge. Well, it's, yeah, worse for the edge, which is why it was abandoned in the 70s and 80s. And we can illustrate that here by looking at some stability properties. So here's a scan of our shape. We're going from positive triangularity in blue to negative triangularity in red. And over the outside of our flux surface, from 85% to 100% of our onion, I'm plotting the pressure gradient, and the shaded region here is an unstable to some MHD mode, some instability. In positive triangularity, where this is blue, there's a gap in the stability right by the edge. If you see the contours for blue here and blue here don't meet. So there's a stable region right in the middle. And this allows the pressure gradient to build up a peak. And if you remember back to our pressure profile, that means a really steep gradient right in the edge, which is how we get into H mode. In negative triangularity, this closes. This red line goes all the way across the outside of our plasma. So these pressure gradients that I've plotted here are actually unstable. And to make them stable, I have to reduce the pressure gradient in the edge. I have to have a stability, a pressure gradient that is stable the whole time. It can't go into the dashed region. So here in this rightmost case, we have now real physical examples. The blue case is a really steep H mode with a gap in stability. The red case, the instability line goes all the way across, and so our pressure gradient is reduced. And so this is bad for the edge because we're reducing our gradient by increasing our transport. We're increasing our stability. We're basically poking holes in this bucket that we liked so much in order to make it worse. Which, why would you want to make your edge worse? Well, if you make your edge bad enough, it turns out you can completely get rid of the elm problem, where we're melting our walls. So in this experiment, which is real data, we have the triangularity up in the top here, and we're very negative to start. Then we go to something positive, and then we go back to negative. And D alpha, which I mentioned earlier is our light, how much light is our elm producing? You can see when we're at a positive triangularity or near zero, we have these big spikes in our light. We have big elms that are going through. This is the same thing. The Q is our heat flux here. We have big heat flux on a diverter. But if you look at cases where it's negative, our elms basically disappear. Our heat flux is stationary and less than the peak here. And so this is a great way to avoid elms and to do so robustly. And this avoidance of elms is really due to this increased instability in the edge, which we used to think was bad. But now we're like, okay, we can poke some holes in a bucket and arrive at a happy medium. It turns out that this phenomenon is not just the property of one discharge. It's really robust over all negative triangularity discharges that we've seen so far. So this is 10,000 data points from the D3D Tokamak in California. And as a function of triangularity, we have our normalized heating power on the y-axis. Anything above this dashed line should have a normalized heating power good enough to go into H mode. So L over H greater than 1, we should be in H mode. We should be elmic. We can see those elms if we go to near zero triangularity. If we go to very negative triangularity, those elms completely disappear. And so there's some examples of what that D alpha trace looks like here. Our D alpha for our slightly negative cases is big and strong. Those are big elms. Those are bad. But if we go to the very negative cases, those completely disappear, and we're left with just a stationary thing sitting there by itself, not making overflowing buckets. And so this is a pretty robust solution to the L problem, and it's all due to this extra transport from these modes in the edge that we're making them stable. There are a couple other strategies to do this. This is not a new problem. We've known about elms since the 90s, and we've come up with a bunch of different strategies to do so. QH, RMP, I mode, EDH mode, L mode, these are all just different acronyms corresponding to some different physics technique that people are using to get rid of the elms. And then on these plots here, we're showing how negative triangularity, which is relatively new, is compared to these old established techniques. So if you look at plot C here, normalized pressure and normalized confinement, the more normalized pressure we have, the better. The more normalized confinement we have, the better. Negative triangularity discharges are way up here at the top, compared maybe to QH mode at the very better. but they're significantly higher in both confinement and pressure than the rest of these plasmas. Same thing if we look at the normalized edge density, again, more density is good for fusion. Negative triangularity gets to really high values and also gets to pretty reasonable values for radiative fraction. Radiative fraction is important because we're trying to radiate some of our power away from the core plasma before it hits the diverter region. If we can get rid of some of it, then we don't have to have a material that withstands as much. And so the higher this number, the better. L mode is really good at highly radiated plasmas, but it's really bad at confinement. It's a low confinement mode. And so negative triangularity hits some sort of middle sweet spot there, which is pretty nice. This is another way to look at the same data. This is a bunch of different criteria that we have to meet simultaneously in order to have a regime run on a reactor. This is data from 2021 comparing all these different strategies. Negative triangularity here is in the middle. You see it's already looking pretty good. After some more recent work that we did last year, it turns out to be really, really good. It can meet all these things. And I put stars here as well to indicate different parameters that we're able to meet simultaneously. So we can't just have low power and have high density at the same time. We have to have high power and high density. And so all these stars are simultaneous axis. We're getting really close to being able to put a full green column here with stars on every axis. So that's pretty exciting. And this is a relatively new regime compared to some of these older strategies. So we've seen that negative triangularity is inherently unfree, which is a great solution to the unproblem. And it also has good performance, comparable sometimes even to H mode. It also offers some practical advantages in the power handling sense. So here's an example of what a negative triangularity tokamak might look like. Again, note it's like an inverted D, where the flat side's on the outside. We can operate at powers coming out less than the power needed to get into H mode. So positive triangularity discharges always have to get into H mode in order to meet their fusion power, which means you always have to have a lot of power coming out, which means you always have to have some huge amount of power meeting your machine walls. The negative triangularity can actually get to the same sort of performance with less power going in, and so that's a great advantage. And then again, because we're at a larger radius, we are afforded some geometric advantages as well, where we have more plasma wetted area out there. We can spread our heat flux over a larger surface so that it's not so concentrated in particular spots. We have more space for a flexible diverting design. We have wider orbits, which is again spreading out our heat flux. There's actually lower magnetic field back there as well, which makes it easier for these coils, which also have to have 19 megaamps, 6 megaamps running in them, to do a good job of shaping the magnetic surfaces in particular ways in that area, because there's less colloidal background magnetic field to worry about. So putting all these things together, we've been working recently to design negative triangularity reactors that could actually make commercial use. And so one of the things I've been working on over the past 2 years is to do this for as a student-led course. So we actually have students at MIT and Columbia all come together for a semester or two. They each get to learn about one particular code, one particular physics problem, and then master that over the course of the semester. And then most of the course is spent with them talking to each other, so they can figure out, oh, I want this, you want that. How do we compromise? And we end up in this pretty cool spot where we have a negative triangularity reactor with good enough ion electron temperatures in the middle in order to sustain a fusion reaction. And there's a paper that just came out last week about this, which is pretty cool, and I can send you after if you'd like. A question in the back?
Yeah.
Yes. So, right, yeah. So there's a question about negative triangularity and cost, and specifically on negative triangularity and the cost of the diverter, which is actually my next slide, so great lead-in. One of the additional reasons people haven't looked at negative triangularity in the past is because it's expected to be a little bit more expensive. The underlying reason for this is because you have a greater amount of your plasma farther away from the core, which means you need magnets that are bigger in order to confine that plasma. And those bigger magnets cost more money. And magnets are actually one of the most expensive things in the fusion power plant. And so what you end up with is, in the standard model, something like this, where you could have capital costs for a bunch of different negative triangularity shots here in red and positive triangularity designs in blue over Q95, which is basically a measure of safety. So you can choose some safety of how much you want your plasma to stay there, choose some value, and then go find your cost. Kind of regardless of what you do, you end up with about 50% more cost for negative triangularity. And conventionally, we think of this as cost for two advantages. One, we don't have elms anymore, which is a huge advantage because elms remember we said we cannot have on a power plant. So you're retiring your physics risk, you're retiring your technological risk for a little bit more cost. It's also compatible with the radiated diverter, which is really huge, because what we don't really know with in positive triangularity designs right now is how to deal with the power, right? And so we might have to do exactly what you're saying, go in and replace the diverter. These machines are quite complicated. I only show the magnetic field coils here and the plasma itself, but there's actually a ton of other components, right? There's diagnostics, there's heating, there's blankets, there's all this other stuff. So going in and extracting a piece of the metal and then replacing it when it melts and replacing it when it melts could be really, really challenging. Likely leads to months and months of downtime for your machine, increases the price of energy, right? You don't want your power plant to turn off for 4 months of the year. So negative triangularity could offer a way to reduce that. By how much, we don't know yet. That's an ongoing study of what that advantage would look like. Yeah, question here.
Time you can sustain a fusion reaction with a fusion bigger than one.
The state of the art at this present moment is like 20 nanoseconds or something. The only machines that have ever done that are inertial confinement fusion machines. And so these are laser pulses that just blast in and they're done. Every tokamak so far has been a physics experiment tokamak. We have not yet built, we are currently building, but we have not yet built a tokamak designed to get Q greater than 1. And so these tokamaks at the moment, yeah, you can't get Q greater than like 0.5 or something like that. We've never actually made it to the ignition region. There are 2 machines, one in France and one, actually 3 now. One in France, one in Massachusetts, and one in China, which are targeting this Q greater than 1 achievement for the tokamaks. And they should turn on. The one in Massachusetts, I think, will be first in like 2026 range. The China and the France ones likely sometime in the 2030s, 2040s. But those will be able to generate Q greater than 1 for the first time ever in a tokamak, and then we'll know what the state of the art is for the pulse. In terms of pulse length on conventional machines at the moment, they're all physics experiments, so they're all designed to do a particular thing. There are tokamaks, for example, the one in Colombia or the one in San Diego that don't operate for more than 5 seconds at a time because they're just trying to do a lot of different pulses, a lot of repetitions to learn something about the science. There are also tokamaks, particularly in Korea, Spain, and China, that are really pushing those boundaries. And so they've had pulses that are several minutes long, and trying to understand what happens to the plasma over the course of several minutes. So I think our record is a few minutes at a reduced confinement and reduced properties. But so far, yeah, nothing in the tokamak sphere is great. It's greater than Q, greater than 1. Sweet. So I think I'm basically done with slides. I wanted to say that negative triangularity is really rapidly expanding across the globe. There's a bunch of experiments now that are looking at this. And if you'd like to get involved, there's actually several ways to do this locally from Colorado. University of Colorado Boulder, of course, is a very strong physics program. Plasma physics is very well respected here as well. And so you can do a lot of great research or a lot of great communication with people here at UC Boulder. CSU up in Fort Collins is growing a laser fusion program, and they're doing so really rapidly. They got a big grant from a private company in Germany and are slated, if that goes through and everything, to become one of the leaders in pushing this laser technology forward to get fast repetition rates, to do ICF on a dime. There's actually a few private companies now, not necessarily based in Colorado, but with offices or with people here, Fiat Lux, TechX, and Thea Energy, which are all looking either at tokamaks or alternative concepts as well. And if you'd like to learn more about any of that, please email me at this address. I'm happy to take questions here, or I think there's cookies as well. We can take questions there. But yeah, thanks for having me.
Just following up.
Yeah.
So what happens to the plasma effect? The space, the holes in the pocket.
Yeah. So what happens to the plasma that escapes through the holes? So it still has to leave. And it's actually quite important that it does as well, because we don't want it to all stay there. If we actually have a fusion machine, we want deuterium and tritium to stay in the core, but then eventually we're going to make helium, and we have to have some way to get the helium out. So all the plasma that leaves goes through the holes in the bucket. It's going to go down through this arrows that we were looking at back here. Maybe it's too far back to show. But it goes down through these arrows and then flies into the diverter region. So the diverter then has a bunch of really strong metal. It has some really high fluence pumping ducts to get rid of the excess gas. And that's really your trash can. These diverters are essential to mitigating buildup of everything throughout your device. And so they're where everything leaves. Good question. Yeah.
So on the last slide, this image of, the negative triangle.
Yeah.
Or the lot. What only thing is that how do you get that out to a device that can make electricity?
Great question. It would take the temperature back, yeah. So how do you turn a hot sun in a magnetic bottle into electricity? It turns out that the tried and true method to do this is to boil water. So we make steam. In a reactor design, what we'll have is we'll have some big blanket on the outside, which is basically a heat transfer between radiation and energy coming out from the plasma into pipes that are just boiling water. Eventually, we'll have some turbine that's pumped by the boiling water. So it's really, I mean, there's a lot of ways to frame this. If I go talk to kids, sometimes I say like, oh, do you know the villain in Spider-Man? Doc Ock, he's trying to like control a sun, and I could be that guy, or I could just be a guy that has a lot of trouble boiling water at home. It's pretty hard. Yeah, in the back. Yeah, so that's a really good question. So the question is, do the holes regulate dynamically how much plasma comes out? Which is really a question of like, how does the plasma turbulence change how much is coming from the core to the edge, right? And that can be a really complicated dynamic. If you remember back to this slide, which I kind of glossed over and told you there are a bunch of other acronyms out there. Each one of these acronyms has a different way to poke holes in the bucket. So they might have some particular type of turbulence that they like, or some particular instability that they're destabilizing. And depending on what that is, it can really influence how your core plasma behaves, how your scrape-off layer power heat fluxes behave, and it's really a bite-by-bite issue. One of the cool things about negative triangularity that I didn't get a chance to say is that the way we poke holes in buckets in negative triangularity is purely geometrical, right? We just changed the shape. And so it's really robust. And most of these other regimes, what you're doing is you're trying to trick the plasma to like create an instability and then hold the instability there without extinguishing itself, and then put in some like 3D magnetic perturbation in order to control that. And it's really tricky. And so when we try to do this on D3D in California, in negative triangularity, we turn the plasma on, plasma does its thing, it turns off, there's no element the whole time. Whereas something like QH mode, it's a 5-second pulse. We might have like 1 second in the middle where it's elm free, but then we lose control of the plasma, right? So they're a little finickier as well. And so depending on what breed of turbulence you're trying to induce in the edge, you can have different levels of robustness. Good question. Yeah.
You talked about cross-section area and 3D half an example.
Yeah.
What was the breakthrough statue?
Yeah, that's a great question. So the question is, how did NIF get their breakthrough, basically, right? NIF is a big laser facility in California that had this big breakthrough in 2022. And actually since then, they've done a lot more work as well. That is really a story of tremendous success in modeling and predictive technology. So what happens in ICF, you have a sphere of frozen deuterium and tritium, and you're trying to compress it from the size of like, comparatively like a yoga ball down to a marble, but your sphere is already like a micron across or something. So really just compressing this thing. And the way they do that is they hit the side of the sphere with lasers, and then the lasers create like a little bit of extra energy, and you have an implosion where you're imploding your sphere on itself by symmetric energy around the outsides. And I mean, simple enough concept in practice, or in principle, but in practice, it's really difficult because any sort of asymmetries in your pellet, any sort of asymmetries in your laser, any sort of reduced coupling between your implosion rate on one side or another side, and you don't have a spherical implosion anymore. And it might just like blast through one side of the pellet, or it might be asymmetric and not be able to heat up everything at the same time. And so what the success story of NIF is that they develop these really incredible computational models with really, really fast dynamics on like the nanosecond timescale to measure these incredible plasmas, and then use that to inform predictive modeling to better their manufacturing techniques for the pellet, to better how their laser couples to the pellet, to better how their laser is symmetrically induced around the pellet to be perfectly spherical. And then the reason it kicks off out of nowhere is because once you get those conditions right, then the plasma kicks in and does a lot of work for you. Right, so the plasma, like we said in the beginning, fusion is really hard to get going. Once you get going, you can kind of just feed it and feed it. in this case, like once it got going, then the plasma helps you along. And so you see this big spike. And then you're in the burning plasma machine where you have another power source. It's really cool.
About this hard to scale, what are they trying to do? Why not for all these users to pull it out?
There's a lot of answers to that. I mean, the simplest level is just it's nice not to have all your eggs in one basket, right? I mean, these have been very long-term research programs, right? A lot of people joke about like, or at least in grad school, we would joke about, oh, who do you think is going to get the Nobel Prize for fusion or something? But this is not a single person effort, right? This is started in the 60s and will continue throughout the 2100s. And a lot of progress on these. And it wasn't obvious at any particular point that this was a better strategy, that was a better strategy. Right? The US actually started with these twisty stellarators because we thought we could build magnets to do it, but then the Russians came in with the tokamak idea. And we're like, oh, that's pretty cool, let's do that. And so the path forward has always been clear, so it's nice to diversify. The other answer is that laser plasmas also get a ton of support for our stockpile stewardship. So these models that we can use to develop really impressive models of how the plasma evolves in a little implosion can also be used to make sure that their nuclear stockpile is okay without having to blow anything up. So there's a big source of overlap there. NIST does not just do laser based fusion. They do a ton of different laser experiments. And fusion's just a small part of their arsenal. Whereas tokamaks are basically just fusion plasma. We're only recently starting in like the past 5 years to try to open this up to space, having people that do space plasma run experiments on the tokamak and stuff like that. We call it frontier science, but it's mostly just been pure fusion all the way through. Yeah.
It's all the neutrons.
Great question. What happens to all the neutrons? So yeah, if you look back at the particular reactions that we were able to have, you'll see that or at least DT, and also one of the DD reactions produces neutrons. And neutrons are inherently dangerous. That's one of the reasons why there's these alternative strategies to try to use like proton boron 11 or something like that to have a neutronic fuel, but their cross sections are smaller, so it's harder. So what happens to neutrons in DT is that they fly out. They just do that, right? So this necessitates a huge amount of shielding around both our magnets, which are high temperature superconductors, which can't withstand that many displacements per atom by bombardment. It also has a bunch of shielding around the blanket tank and around the whole machine itself, just concrete mostly, except in certain scenarios. And the neutrons just get absorbed there. This is actually the biggest source of radioactive waste in tokamaks and fusion experiments is neutron bombarded concrete. And so we end up with slightly radioactive concrete after some time. This will likely lead either to a necessity to replace stuff over and over again, or a finite lifetime of the plant or something like that. But there's also strategies people are thinking of starting something in DT and then moving into DD or moving into D helium-3, right? If you're making helium in your tokamak reactor, perhaps you can use that and like use your power that you already have going to kind of transition you into an neutronic thing. There's a lot of advanced strategies there. Those are all, I think, more like second generation tokamak strategies. The first one's just going to be, we'll have some radioactive concrete. Any other questions? Yeah.
If you're deteriorating, I'm sure you get ejected into this strong magnetic field. You start turning, and I start turning. In our frames of reference, we're just moving around side by side. How do they collide?
Yeah, good question. So, plasma is less like a smooth river and more like just a hot, messy soup. So we have these nice flux surfaces that we're going along, but they're actually nested flux surfaces like an onion. So it's not just one line, it's a whole surface. So I'm exposed to everything on the surface. I'm also drifting around that surface with a particular gyro radius. And so I'm interacting with other surfaces and particles on other surfaces as well. And so I'm interacting across layers of the onion. And we're going different directions. So there might be some plasma streaming this way and some plasma streaming that way. And that can all leads to a hot, messy soup. We're not all in sync. We're not acrobats. We're just going in every which way. For some context, like the rotation speeds of plasma inside of tokamaks are on the order of like thousands of kilometers per second. So stuff is going really quick and spinning really fast. Yeah. Yeah.
Oh, I know this sort of problem where they really have the problem solved. What are these barriers to all engineering? Are there problems?
Yeah, great question. So ITER is a big tokamak in France. It's one of the three that I was talking about that should be able to get break even. It was started a long time ago when we didn't know if big magnets were a technology that you could ever have. And so if you don't have big magnets in tokamaks, you have to have big size. And so ITER got really big. And it's also because it was a great collaborative global effort. It turns out that the ITER organization is made up of many different member countries, all of which have to communicate with each other and have their own grants and their own blah, blah, blah. And so it can get really tricky to find a schedule there. So the real slowdowns with ITER are mostly in the geopolitical organization of the organization itself. It's by any measure of like scientific scale, the largest international collaborative science experiment that we've ever tried to build on Earth. And that's hard. There's been a lot of learning that went along just on the political side of ITER. They've also had a couple unfortunate things break during the process, and so I've set them back here and there. But the real story as well is that over the course of when ITER was being built, we've discovered high temperature superconductors, which let us get to high magnets. And so this gives us a different strategy. We don't have to go super large. We can actually build a smaller machine just with stronger magnetic fields to keep the plasma there. And that's what the machine in Boston or in Massachusetts is trying to do. So they're moving a lot faster. They're one private company, so everything's internal. They can just streamline. Cool. Thanks for the interaction, and it's my pleasure.